Example 4, so solve. This one looks a little bit different because now on the right side, we actually have a multiplication between two terms or two factors. But the same strategy, change a base, make them all the same. We kind of gave you a hint here, there's a 2. So 2 to the power of 4 is 16. We still have that 3x exponent. This is already a base 2. And then 2 cubed is 8. And we still have the 2x exponent. Now we've got a choice here. We could simplify this right now and go add these two together. Or we could make this equal to each other with the acknowledgement that this is actually going to be an addition between this and this. I'm going to do the second. So we're going to get 4 times 3x is equal to 5x plus 2 plus 3 times 2x. You could put brackets here. It would matter a lot more if this was a subtraction between these two. So if this was a division. For addition, it doesn't really matter too much though. Okay, so let's simplify as much as possible. So on the left side we have 12x, and on the right side we have 5x plus, well, the 3 times 2 is 6, so we get 11x plus 2. I'll subtract 11x from both sides. We get x is equal to 2. Let's do the right side question then. So again, we have 27 as a base, 3 and 9, so we need to make the base the same. So 3 cubed is 27, so we have x plus 1. And then here we already have a base of 3. And then 3 squared is 9, and we still have that x plus 3 exponent. All right, we're going to make all of these equal to each other then. I'll do the distributive property now, so 3x plus 3. Here we have x minus 3. Now between these two exponents, this would have been an addition, so we'll go plus, and then 2x plus 6. Combine some like terms, and we get 3x plus 3. Uh-oh. Well, the left side is equal to the right side already, which isn't a good sign, because if I go and subtract 3x off both sides, I'm going to find out that 3 is equal to 3, which is true. And so here we actually have a case of infinite answers. These are actually the same graph, the exact same graph. So for any value of x, they will be equal to each other. Well, let's throw some square roots in here and see how you feel about that. Well, not even square roots, fourth roots and cube roots. The strategy stays the same. We still want the same base. So it's not very obvious right here, but we gotta look at the numbers 64 and 4. They can both be written as a power of 2. So 2 to the power of 6 is 64, and we still have that x minus 2. The right side's a little trickier. I'm going to do this in a couple steps, so I'll leave this to the power, or to the fourth root. And 2 to the power of 2 is 4. And this is still all to the power of 3x plus 3. So I'll do the distributive property here, so 6x minus 12. Over here, I'm going to use flower power. So I have 2 to the power of 2 with a root of 4. And that's going to be multiplied by 3x plus 3. There we go. Now we have the same base, and we can actually make the exponents equal to each other. So we get 6x minus 12. I'll distribute this right now. This is really 1/2, so it becomes 3x over 2 plus 3 over 2. I'm going to make this a little bit easier by just getting rid of these fractions. So I'm going to multiply everything by 2. So I get 12x minus 24 equals 3x plus 3. I'll subtract 3x off both sides, so I get 9x on the left side, and then I'll add 24 to both sides, so I get 27 on the right side. Divide both sides by 9, and we get x is equal to 3. Let's take a look at the second question then. So we've got a base 3 on the left side, and potentially we've got a 9 here as our base. So they can both be made into a base of 3. So on the left side, we'll leave that one alone. And I'm going to do this one a little bit differently. So 3 squared is 9, but a cube root can actually be written as to the power of 1/3. And then all of that can be written to the power of 2x plus 4. So now we have the same base, and we can make all of the exponents equal to each other. So 4x is equal to, now these exponents right now should be multiplied. So in my equation, they are going to be multiplied. So 2 times 1/3 times 2x plus 4. So we'll simplify this as much as we can. So 2 times 1/3 is 2/3. And then I'm going to distribute this 2/3. So we get 4x over 3 plus 8x over 3. I think it's going to be a little bit easier if we just get rid of all these fractions. So I'm going to multiply everything by 3. So I get 12x equals 4x plus 8. Subtract 4x off of each side. So we get 8x equals 8. Divide both sides by 8, and we get x is equal to 1. All right, example 6, a completely different type of question. A nice fun one. So we have 2 to the power of x plus 3 plus 2 to the power of x plus 4 equals 96. Well, the problem here is we can't use exponent laws when we've got an addition. So that completely changes how we have to think about this question. And so what I'm going to do then is I'm actually going to split apart this x plus 3 here. Because really what this means is 2x, 2 to the power of x, times 2 to the power of 3. So if you remember, when you have the same base and we're multiplying, we actually add the exponents. So that's what's happening there. And we'll do the same thing here. We have 2 to the power of x times 2 to the power of 4 equals 96. Well, I actually have a GCF here of 2x. So I'm going to factor out the 2x. So I'm going to be left with 2 cubed plus 2 to the power of 4. Well, 2 cubed plus 2 to the power of 4 is 24. So we get 2 to the power of x times 24 equals 96. So I'm going to divide both sides by 24. I get 4. And then we'll make it so the base is the same. So 4 is actually 2 squared. And therefore x is equal to 2. So a fun little question. Example 7. Solve. 3x equals 7. There's no common base between 3 and 7 that I can make. So how am I supposed to solve this then? Well, you can't. Not yet anyway. So you'd have to use logarithms to be able to figure this out. If we're going to do it algebraically, you could do guess and check, or you could use your calculator and do the graphing method. We're going to do the graphing method here. So we'll go 3 exponent x, and then we'll put our right side as our y3. We'll graph that. And our intersection points, so second trace, we want the intersection, so that's 5. Enter, enter, enter. Intersection point, 1.77. So we're down to the nearest hundred, so therefore x is equal to 1.77. So right now, that's all you're going to do if that happens. Our second equation is the same problem. Yeah, we could turn 4 into 2 to the power of 2. Doesn't help us though, because 6 is never going to be a base of 2. So we're going to go back to the calculator one more time. Clear these out from the last question. So we have 2 times 4 to the power of x minus 1. Now if you're using a TI-83, you're going to have to put brackets on that x minus 1. And then for y2, we have just 6. So we're going to graph that. And again, looking for the intersection point, so second trace. And then 5 is our intersect. And make it enter, enter, enter. And we have an intersection point of 1.79. So therefore, x is equal to 1.79. And that's it.